I'm Santoshkumar, research scholar in the Department of Electrical and Electronics Engineering, National Institute of Technology, Karnataka, Surat. My research supervisor is Professor Uday Kumar. The presentation is on the topic Performance Investigation of Mobile WiMAX Protocol for Aggregator and Electrical Vehicle Communication in Vehicle to Grid. The contents of the presentation are: Introduction. Vehicle to grid concept has become a reality due to the advancements in the power grid and recent developments in the electric vehicle technology. V2G is also considered as a distributed resource. V2G plays a prominent role in meeting the load demands. It can sell power to the grid or buy power from the grid. So that is how it is meeting the load demands. Usually the electrical vehicles are parked for 90 to 95% of the time. The V2G is economical, efficient and effective. The battery charge is very important. The battery of the electrical vehicle is very important. The state of the charge of the battery is very crucial. If the state of the charge of the battery is in between 20 to 95%, the battery life will be good and the performance of the battery will improve. If the state of the charge of the battery is in between 40 to 90%, then the vehicle can be connected to the grid to sell the power. If the battery charge, that is the state of the charge of the battery, is less than 20%, the battery should be charged. That is, the vehicle should draw power from the grid. So the state of the charge is dictating the terms whether to sell the power to the grid or buy power from the grid. In case of vehicle to grid communication, we come across three components: the grid control center GCC, the aggregator and the electrical vehicle. The grid control center to aggregator and aggregator to EV. So aggregator acts as interface between a grid control center and the electrical vehicle. Aggregator will send the information to the electrical vehicles. The responsibility of aggregator is to mobilize the vehicles and bring it to the charging station. The grid control center will send the information about the electricity requirements to the aggregator. The aggregator in turn communicates with the EVs. It will invite electric vehicles and it will invite them to sell power to the grid. So aggregator will send the messages to the vehicles whether they are in motion or they are parked in a parking station. The components of the V2G are listed here. The figure shows the components of the V2G. So this is an electrical vehicle. This is the grid. This is the smart meter. The electrical vehicle is connected to this grid. Either the electrical vehicle can sell power, that is V2G, or it can draw power from the grid. Smart meter is the one which is communicating to the electrical vehicle. So the bi-directional way of communication is possible with respect to this smart meter, and it is communicating to this particular electrical vehicle. The vehicle can be connected to the charging locations, either home, apartment, garage, commercial buildings, station, etc. So this is the complete picture of vehicle being connected to the grid and the components, the aggregator and the ISO. So this is the picture of a V2G, or like vehicle connected to the grid. The system model of V2G. Here, as already you discussed, there are three important things in case of V2G communication: the smart grid control center, the aggregator and the electrical vehicle. The information should be broadcasted from this grid control center to the aggregator using the wireless network, and from the aggregator to the EVs using the wireless communication protocol. So the information from this end to this end and the information from this end to this end should be wireless. So in our presentation, we are concentrating on this particular concept. We are thinking of communicating from aggregator to the vehicle in a wireless way. So role of ICT. ICT plays a key role in communication. GCC, that is grid control center to aggregator, and aggregator to EV communication is very crucial. Communication is required for smart charging and discharging. So before getting into the details of path loss models, basically we investigate the path loss models once we are working out for the wireless communication protocols. So information, if it is being propagated, the signals which are being propagated will come across a lot of obstacles. Due to that obstacles, the signal gets faded. That is called as fading. So in order to work out for the fading and the loss in the strength of the signal, we work out for the path loss models. The path loss models calculate the electrical field strength and predict the path loss. And this prediction of the path loss is very important in planning the wireless network. The information is propagated by means of electromagnetic waves. The signals come across a lot of obstacles in the environment which causes path loss, as discussed earlier. So difference between the transmitted power and the received power is measured in decibels, is called as path loss. So the path loss is an important factor while deciding or planning the wireless network. So the path loss is categorized into three parts: the deterministic, empirical and stochastic. Deterministic is site specific. It is dependent on the geographical location of the environment, whereas empirical is based on the measurements. At the same time, it is based on the antenna height, distance and the frequency. Stochastic process use series of random variables to model the environment. So we usually work on the empirical models, and basically we use these empirical models to model the path losses, to work out for the path loss models. So these are the path loss models which we have covered in our study, or which we have simulated, wherein we have analyzed and compared with the help of simulation results. The free space path loss is the ideal or realistic model. That is the one which will be always taken in order to compare it with the other models. The COS 231 ATA model is well suitable for urban areas, and it is for the frequencies 1500 MHz to the 2000 MHz. Then Stanford University Interim SUI model is developed by the Stanford University, and it is a de facto standard of IEEE WiMAX. Then Hatao-Kumara is most externally used for the frequency greater than 3 GHz. Then COS 231 WI model is suitable for the environment wherein the buildings are uniform. Ericsson model is also suitable for the urban areas. So the empirical formulas are picked for the simulation purpose, and we have analyzed, compared using these empirical formulas. Then after working out for the path loss models, we have to think of the concepts of wireless connectivity, wireless communication. What all things have been already addressed in case of wireless communication for a vehicle to grid when it is connected to the smart grid, V2G when it is connected to the smart grid. Many researchers have worked on Bluetooth for V2G connection to the smart grid. Researchers have also investigated the Zigbee protocol. They have worked out for the Wi-Fi. The fixed WiMAX is applied to the grid control center and the aggregator. And in our work, we thought of working for the aggregator and we thought of working for the communication protocol which will address the aggregator and the EV communication. So we thought of taking into account the mobile WiMAX, which is well suitable for our application for the communication between the aggregator and the electrical vehicle. The WiMAX standard defines air interface for the frequency range 2 to 6 GHz. The ideal characteristics are it supports 50 km coverage area and data flow up to 70 megabits per second. So this is the ideal characteristic of a WiMAX, but in practice the coverage area is 5 to 7 km and 7 megabits per second. So this sounds reasonably good for our application, as the aggregator and the electrical vehicle, they will be placed either within the radius of 5 kilometers or within the radius of 7 kilometers. So the range is 5 to 7 kilometers. So we are working with the 5 to 7 kilometer and the 7 megabits per second. That's the mobile WiMAX. This is the basic block diagram of our mobile WiMAX. This is the transmitter, this is the channel, this is the receiver. So transmitter, the receiver and the channel. Communication channel is very crucial in order to address the issues with respect to communication channel, we had to work out for the noise related environments and to solve so many, like we need to address a lot of issues here also in case of communication channel. So we have worked on the basic mobile WiMAX model. So this is the digital transmission process wherein we come across the bits. Bits are transformed or converted to symbols. Symbols are converted to pulses. Pulses are being propagated. Pulses are converted to symbols and symbols back to bits. So if you look at bits to symbols, it's a discrete domain, and symbols to bits, it's a discrete domain. The transfer of the information through the channel, that is continuous time. So this is the one wherein digital transmission process takes place. The source of information is this, the destination is, the information which is received as a destination is this. So we are going to evaluate, like you check out whether the errors have been introduced in this particular bits. So functional stages of WiMAX. This is the frequency domain and this is the time domain. If I go for IFFT, then the frequency domain components will be converted to or transformed to the time domain. We analyze the signals in the time domain. So this is the basic functional stage of a WiMAX, and these blocks are used in the WiMAX protocol. This is a basic OFDM symbol. The cyclic prefix are the P symbols which are repeated here. So this will help us to rule out the inter-symbol interference which will occur. So there are block of N data symbols. There are P symbols. So every frame what we take, it will have this kind of repeated P symbols. The OFDM symbol has three things. The data for data carriers or transferring the data, the pilots for keeping track or estimating the channel, and synchronization. So channel tracking, estimation and synchronization can be done using these pilots. The guard bands are used to provide frequency guards between the, like they are used to safeguard the symbol. That is, we are going to work out for reducing that ISI using those kind of bits, guard bits. Multipath caused by reflection. So if you look at the transmitter here, there is a mobile, the information which is transmitted directly, and you can look at the other signal which is wherein it is coming across obstacle, it is reflected back and receiving the mobile, like it is reaching the mobile, at the same time it is reflected by the vehicle. So this is alright, but these are the ones which will create a problem. So that is called as multipath fading. So it has to traverse through the multipaths. So multipath induced time delays. Here, if it is a direct thing, the signal will reach here. But if it is through these multipaths, the signal will reach here. So the time which is responsible for this will induce the ISIs. So this is not accepted. So it is inter-symbol interference. Now, frequency selective fading, the signal bandwidth, there are large deep fades in this signal bandwidth. So this is due to the multipath distortion. In order to address this, we come across the OFDM or OFDMA. So mobile WiMAX is based on OFDMA. OFDMA allows for sub-channelization of data in both uplink and downlink. Sub-channels are just subsets of the radio carriers. They can use contiguous or randomly allocated frequencies. Now, OFDM symbol period. This is the symbol period. This is the cyclic prefix symbol period, cyclic prefix symbol period. So one thing we need to notice here, that the symbol period, longer symbol period and the cyclic prefix will rule out the ISI. So it will eliminate the ISI. Whereas in case of single carrier, the delay induced by multipath can cause the symbol received along a delayed path to bleed into the subsequent symbols. It is bleeding into. So this is how the OFDM is eliminating ISI, and the cyclic prefix and the FFT period are the two components of the OFDM symbol. So this is the IEEE 802.16 for n equal to 256. There are three things: data, pilots and nulls. The data is being sent. So IFT, FFT. Here the frequency domain. After this we get the signals in the time domain. That is a transformation from the frequency domain to the time domain. So x of k to x of n plus of n. Results and discussion. We have considered the path loss simulation parameters in order to simulate it. The distance between the aggregator and the EV is 5 km. Aggregator acts as a transmitter, EV acts as a receiver. The transmitter antenna height is 30 meter and the receiver antenna height is 6 or 10 meters. So these are three things which we need to take care of. And the mobile transmitter power is 30 decibel meter. Then the transmitter, like the building to building height is 50 meters for the simulation purpose. If you look at the curves here, the path loss versus distance between aggregator and EV in kilometers, it is still 5 kilometers. And we have investigated the path, we have analyzed and compared the path loss models. This is free space, idealistic or realistic, ideal or realistic. Here, if you look at the SUI and Ericsson, as the distance increases, the SUI and Ericsson work hand in hand. That is, Ericsson is bit less as compared to the SUI. So SUI and Ericsson are found to be better as the distance increases. Those are the path loss models. And if you look at these two path loss models, the cost theta and cost WI, the path loss which is observed is around 165 decibels or 167 decibels. So these two things are on the higher side. But if you look at ECC 31, it is falling in between these two. So it is moderate. It is exhibiting the moderate performance. So Ericsson, then the SUI and the Ericsson are demonstrating lesser path loss as compared to other path loss models. So in case of WiMAX, the de facto standard which is chosen is SUI itself, because it can be applied to urban, suburban or hill regions. The path loss estimated at 3 km distance for the urban, if you look at, the strong contenders are SUI and Ericsson. And if you look at the 10 meter receiver antenna height, once again the SUI and Ericsson are the strong contenders. But if you look at the suburban area, the SUI sounds better in both 6 meter receiver antenna height and 10 meter receiver antenna height. At the same time, we thought of simulating SUI separately for the WiMAX, as it is a de facto standard available. So these are the simulated results for the RXC model or the SUI model which is adopted. Then we thought of working for the WiMAX. WiMAX was simulated in MATLAB, and we consider these four modulation schemes. The bit error rate versus SNR plots were, the graphs were plotted for that. We are interested in the bit error rate as well as the SNR. So if you look at the BR versus SNR, these plots will give you the clear information. That is, there is always a trade-off between the power, the bandwidth and the BER. So in order to say achieve 10 raised to minus 1 bit error rate should be always lesser. In order to achieve the 10 raised to minus 1 bit error rate, the QPSK demonstrates 6 decibels. Whereas in order to achieve the same 10 raised to minus 1, the QAM, 16 QAM demonstrate 8, and the 16 QAM 3 by 4 demonstrate 10. The 16 QAM demonstrate 10 decibels, whereas this particular QAM demonstrate 8 decibels, and if you look at 10 raised to minus 1 for this, it demonstrates around 12 decibels. So we are interested in achieving this. So if you look at the SNR, it is 6, 8, 10 and 12. So this is the one which is speaking with respect to power. This is the one which is speaking with respect to the bit error rate. This should be less. This should be usually less. But in order to make less, you should not compromise on quality, or you should not compromise on any other things. So we are supposed to work out for this. So coding has been done. We have plotted BR versus SNR, and the results obtained are promising for the mobile WiMAX. The conclusion is the propagation path loss models are analyzed and compared. The mobile WiMAX is considered for aggregator and the EV communication, and the physical layer is simulated. The graph of BR versus SNR is plotted to investigate the performance. The future work, the simulation is carried out taking into account the aggregator to 1 dB, but this can be extended to multiple EVs, one aggregator and multiple EVs. The results can be validated using the hardware, either DSP chips or FPGAs can be considered for the same. Thank you.